In this video lecture, we're going to learn the different factors that are going to affect how ionization energy, whether ionization energy is going to be high or low. And remember, we've previously discussed what ionization energy is. It's the energy required to remove an electron. So, how would that affect different ionization energies of different atoms? So I'm going to draw, and I'm going to pick that example of sodium again, and I'm going to draw a sodium atom again, and it had 11 electrons. So there were 2 electrons in the first shell, and there were 8 electrons in this second shell, and there was only 1 electron in the last third shell. So I'm going to draw that shell now. So that's your sodium atom. Now remember, we're trying to remove electrons over here. So and we're going to assess what are the factors that are going to affect how difficult or easy removing an electron is going to be. So the number one factor is, and the first thing that we need to know is that there is a positive nucleus. If I rub this off, if I rub this sodium off, sodium had 11 protons. So there are 11 positively charged protons that are attracting all these electrons. So the reason why these electrons are being attracted is because the positively charged protons are attracting all these electrons towards the nucleus. So the number one factor that's going to affect ionization energy is that it's going to be the positive charge on the nucleus. So let me write that down. So the first factor is the nuclear charge. So that's your first factor. In other words, in simpler words, I can also state that it's the number of protons in the nucleus. So if the number of protons is high, it's difficult to remove an electron, because the higher the number of protons, the more is going to be the force of attraction between the electrons and the nucleus. So if you have more protons, then that would be proportional to a higher ionization energy. A higher ionization energy. The reason being the nucleus, the positively charged nucleus, is attracting all those electrons. And if you increase the number of protons, there's more positive charge in the center over here, and that's going to lead to a higher force of attraction for the electron. So it's going to become more difficult to remove an electron. And I can do a comparison of sodium, and let's keep all the other factors. Let's ignore all the other factors for a second, and I'm going to draw a chlorine atom. Now chlorine, on the other hand, has 17 protons. So it has a lot higher nuclear charge. So it has 17 protons. This one over here is of sodium, which is 11 and 23. And now I'm going to draw chlorine. And chlorine is 17 and 35. Now one thing that you can clearly see is that chlorine has a lot higher proton number. So in the center of this atom, there would be protons, and there would be 17 protons. So in the center, the nuclear charge is plus 17. There are 17 protons, and all the electrons, the 17 electrons are surrounding these 17 protons. They are attracted by this. So the first shell is going to again have 2 electrons. Then you're going to have then you're going to have 8 electrons in this second shell, and the last shell is going to have a total of 7 electrons. Now compared to sodium, since chlorine has more protons, and let's only focus on this particular point. There would be many other points. So chlorine has a higher nuclear charge. So this over here has a higher nuclear charge. Hence, there would be more force of attraction for the electron, so it's more difficult to remove an electron. So more energy would be required to remove an electron. Hence, the ionization energy is going to be really high. So ionization energy or the energy required to remove an electron is higher. And I'm only focusing on one factor right now. There are other factors as well that would be brought into account one by one. So let's just focus on one factor. So whenever you have two atoms and one atom has a higher nuclear charge, then that means that atom, based on this particular factor, would be more difficult to remove an electron from that particular atom. The second factor that's going to affect ionization energies is called the shilling effect. And let me first explain to you what a shilling effect is by drawing two atoms. And I'm going to take lithium. Lithium has 3 protons and 7 nucleons, so that means it has 3 protons and 3 electrons. So I'm going to draw lithium first. So if I draw lithium, and I'm going to ignore all the other factors. The first factor that we have already discussed, we're not going to discuss nuclear charge in this. We're going to create an overall picture right at the end once we have gone through all these factors individually and then count for them in a combined way. So lithium has 2 electrons in the first shell. So there are 2 electrons in lithium's first shell. And there's 1 electron in lithium's last shell. And I'm going to compare that with sodium. Now if I draw sodium, now sodium has 11 and 23. Sodium is also in group 1. So sodium has a total of 11 electrons. So I'm going to draw sodium now. It's going to be a sodium nucleus in the center. And there would be 2 electrons in the first shell. And they're going to be 8 electrons in sodium's second shell. And there's just 1 electron in sodium's last shell. Now we're going to figure out whose ionization energy and what does shilling effect mean. So ionization energy is the ability or the energy required to remove an electron. So I'm going to try and remove this particular electron that I'm shading in red from both atoms. Now if you look at this electron, these electrons are attracted to the nucleus in the center. So this electron is attracted to the nucleus in the center. This electron is also attracted to the nucleus in the center. Now if you look carefully, observe carefully, and I'm going to highlight these other electrons by blue. So if you look carefully, there are only 2 electrons that are coming in between the electron and the nucleus. So if I can redraw this, there's a positive nucleus over here, and your electron is over here, and these two are trying to attract each other. So let's say this is the force of attraction that's between them. And there are 2 electrons coming right in the middle, and these 2 electrons are creating a blockade. They're blocking the positive nucleus from attracting the electron. So there's a kind of a barrier that's coming in between them, and this is going to decrease the force of attraction between the electron and the positive nucleus. The same is probably going to happen with sodium as well, but there's one slight difference between sodium and lithium. And that difference is, again, there's a positive nucleus in the center, which is somewhere over here. And that's attracting the electron on the outside. So that's the electron over here. And there's a force of attraction between them, an electrostatic force of attraction that is attracting these electrons. Now, in this case, the difference is now you have, instead of two electrons, as in lithium's case, there are four electrons that are coming in between, because there are sodium has more shells. So that's electrons coming in between from the first shell, and these are the electrons that are coming in between from the second shell. Now, if you look carefully, observe carefully, the problem is that you have twice the shielding. There is blockade coming between, so the force of attraction between the electron is going to decrease. So shielding, in simple terms, whenever you talk about shielding, what that means is, it basically means the number of shells between the nucleus and the outermost electron, or it's basically the electron that you're trying to remove. As the number of shells grow, as you have more and more shells, you have bigger atoms. Bigger atoms are going to have more shells. So the shielding effect is going to increase. So the shielding effect basically decreases the force of attraction between the positive nucleus and the electron that's lying on the outer side. As more shells come in between these positive nucleus and the outer electron, the force of attraction is going to subsequently decrease. So the rule for shielding is that as shielding increases, the electron would be less attracted. So this electron, and I'm only talking about shielding right now. I'm not discussing any other factors. So this electron would have a lower attraction, and based on only this factor, the shielding effect, this electron is going to be having more attraction because it has lesser shielding. So as shielding increases, the attraction is going to decrease. It's going to become easier to remove an electron. So it's going to become easier to remove an electron, which means that you would require lesser energy to remove an electron. So ionization energy would decrease. So your ionization energy eventually decreases. So lower attraction and less energy would be required to remove an electron. So ionization energy decreases. So you can say, as the number of shells grow, it's going to become easier and easier to remove an electron. So for bigger atoms which have more shells, the outer electron, it's going to become a lot easier to remove. The third factor that we're going to discuss is distance from the nucleus. And this is very similar to shielding that we discussed earlier. Now, if you look carefully, and we're only going to focus on the distance from the nucleus, we're not going to talk about the other two factors that we've just discussed, shielding and protons. So we're only singling out this factor. So if I try to remove this electron over here, which is this one, or now this electron over here is very close to the nucleus, or which is at the center of the atom. So it's very close to the nucleus. So it has less distance. And since it has less distance, that means that it would be easy to remove this electron. So it's easier to remove this electron. The third factor that we're going to discuss is a distance from the nucleus, which is going to affect the ionization energy. And this is similar to shielding. It's generally very similar to shielding. What this factor is, if I try to remove this electron over here, the one that is represented by this arrow over here. Now this electron is very, very close to the nucleus. I'm comparing it with this other atom of magnesium that I have over here. And if I try to remove this outer electron in magnesium, now this electron is further away from the nucleus. Now remember one thing, we're only focusing on distance. We're not talking about nuclear charge, and we're not talking about shielding. So just focus on distance. Now this electron is very close. It's and I'm comparing these two atoms, so it's comparatively close to the nucleus. And if it's close to the nucleus, that would mean that the force of attraction is stronger. So it's going to be strongly attracted to the nucleus. The further away it is from the nucleus, the weaker the force of attraction is going to be. So there's a stronger force of attraction, which means it's harder to remove this electron. You would need a lot more ionization energy. So ionization energy in this case is going to be higher. So you're going to have higher ionization energy. Now compare this with this other atom over here, which is magnesium. Now this electron is further away from the nucleus, so it's far from the nucleus. Comparatively, that is far from the nucleus. Which would mean that there's weaker force of attraction. The further away you are, the less attraction is going to be. So it has a weaker force of attraction. Now that would mean that it's going to be a lot easier to remove this electron. So you wouldn't require a lot of energy to remove this electron. So ionization energy in this case is lower. So ionization energy is lower. And we can sum this up that if distance is more, if an atom is further away from the nucleus and there's more distance, so if distance is more, then that would mean that the ionization energy is less. So you'll have lesser ionization energy, and vice versa. So that sums up your third point, that if distance is more, if an electron is further away from the nucleus, then it's easier to remove that particular electron. So you would require less energy, so the ionization energy is going to be less. One other way to describe this is sometimes you use the term atomic radius to describe or give the same idea of distance. So interchangeably, what you can use the word atomic radius, and we can say that if the atomic radius is small, if there's a smaller atom, so distance is going to be small, so ionization energy is going to be more, or vice versa. If the atomic radius is more, that means distance is more, then the ionization energy is going to be less. The fourth factor that we're going to discuss has to do with orbital arrangement, or it's basically the orbital arrangement of the outermost orbitals. Now there are 2 points to it. One is that the first one is that if the orbitals are in exactly the same shell, for example, you're comparing 3s, 3p and 3d orbitals. Now these are exactly in the same shell, so there's not going to be a lot of difference between the energy levels of these three orbitals or subshells. Now the problem is, if you're removing an electron, there's some slight difference, which is that 3d orbital is going to be at a slightly higher energy, and the 3s orbital is going to be at a slightly lower energy. So if you try to compare the energy levels of these three orbitals, which are supposed to be in the same shell, the 3D subshell, or the orbitals in the 3D subshell, they would have a slightly higher energy compared to the 3s orbital. Now remember one thing, that when you're trying to remove electrons, if you're trying to remove electrons from the 3D orbital, since the electron already has a slightly more energy, so this would require less energy. That means that it would be easier to remove an electron from the 3D orbital compared to the 3s orbital. So that means that based on orbital arrangement, the 3D orbital would have removing an electron from the 3D orbital would have a slightly lower ionization energy, and this is just a very slight difference. And the 3s orbital, because it is at a lower energy, the electron is going to be less energetic, so you would have to give it slightly more energy when you're trying to remove that electron. So the ionization energy for the 3s orbital is going to be slightly higher. So higher ionization energy. So whenever you're comparing orbitals, and you're factoring in the fact that different atoms can have different orbital arrangements, so removing an electron from the d orbital would be slightly easier compared to removing an electron from the s orbital, and so on. So that's your first point when you're talking about orbital arrangement. The second point is that your second point is that if you're removing electrons from the same orbital, for example, I'm removing an electron from a 3s2 orbital, a full 3s2 orbital, which means that the electrons are paired, and I'm comparing that with removing an electron from a 3s1 orbital, which means that the electron is unpaired. So I have two atoms. In one, you're removing an electron from the 3s2 orbital, and the other you're removing an electron from the 3s1 orbital. Now remember one thing, that when you're trying to remove an electron from the 3s2 orbital, there would be more electron-electron repulsion. So both electrons would be repelling each other because they are existing in the same region and they are both repelling each other. Whereas there won't be any electron repulsion in the 3s1 orbital because there's only one electron, there's no other electron to repel it. So this is called spin pair repulsion. The term given to this is called spin pair repulsion, which means that both the electrons which are paired are repelling each other. Now since they're repelling each other, so it would be easier to remove an electron from the 3s2 orbital or a paired orbital because the other electron would be repelling it from the other side. So it's easier to remove an electron Hence, removing an electron from a fully paired orbital is going to be easier, which means that it's going to have a lower ionization energy. And you won't be giving it a lot of energy because the other electron is already repelling it. So it's easier to remove an electron from this orbital. So these are your 2 points, and these would only be discussed in certain cases because these two factors, the orbital arrangement factor, is not a very dominating factor. So you're not going to discuss this in a lot of atoms when you're comparing ionization energies. The only 2 places where it is going to be compared, or one place it's going to be compared, is when the 2 atoms which are almost similar, where all the other factors are almost the same, and they have almost the same number of protons, the nuclear charge is almost the same. That means that the nuclear charge, there's not a lot of difference. There's only a difference of 1 proton. The shilling is the same, the distance is the same. So when almost all the factors are similar, then you look into these minor differences which result from orbital arrangement. So there are two factors when you whenever you discuss orbital arrangement. That's number one is that the s, p, and d orbitals. The d orbital is going to be at a higher energy level compared to the s orbital. So it's going to be easier to remove an electron because the electron is already energetic enough. So you don't need to give it a lot of energy. And the second factor is that a paired orbital, due to spin pair repulsion, this spin pair repulsion over here, since both electrons are repelling each other, it's going to be easier to remove an electron from a fully paired orbital compared to an unpaired orbital. The fifth point is the positive charge on ion. And this is the fifth and the last factor that's going to affect the ionization energy. So if you're removing an electron, let's say I'm removing an electron from sodium. Now sodium is neutral. It has zero charge. And this is a gaseous sodium atom. So if I try to remove an electron, I subtract one electron, I'm going to get Na1 plus. And that's going to be a gaseous atom as well. Now, removing an electron from an atom that has zero charge, it's going to be slightly easier compared to this second case, where let's say sodium has a positive ion. We're talking about the second ionization energy over here. Now, this one is a +1 ion. A positive ion is going to attract electrons. So removing an electron is going to become more difficult because now sodium is attracting electrons more strongly. It now has an overall positive charge. So when you try to remove an electron from sodium 1 plus, you're going to get sodium 2 plus. And let's ignore all the other factors and let's just focus on this positive charge on ion. Let's ignore all the other four factors that we just studied. This would mean that as the positive charge on the ion increases, as you keep on removing electrons, the positive charge on the ion is going to increase. So as it increases, it's going to become harder and harder to remove an electron. So if I try to remove an electron from sodium 2 plus, this 2 plus is going to have an even higher attraction for electrons. It's going to become even difficult to remove an electron. So the fact is, this fifth factor is that as the positive charge on the ion increases, so removing electrons becomes more difficult. Becomes more difficult. Which eventually means that the ionization energy keeps on increasing. You need more and more energy to remove an electron as the positive charge on ion increases. So the higher the positive charge, the more difficult it's going to be to remove an electron. So just focusing on this point alone and ignoring all the other points, that's the effect of the positive charge on the ion. So there are 5 factors that are in total going to affect ionization energy. So in the next segment, or in the next lecture, we are going to discuss how all these 5 factors combined are going to affect the overall ionization energy of a particular atom.